All right, good afternoon, or welcome back.
Afternoon.
Somehow it's week 4 already, which doesn't seem possible.
Right?
Yeah, it's like it's going to be graduation soon. All right, well, hope everyone's doing well. If I didn't see you in 224, hope you had a good weekend. And I am at a new location, so I just moved into a house over the weekend, and I think my internet is solid here, which is good. So I'm going to go ahead and mute everyone's microphone, and then if you want to talk, go ahead and unmute. And so let's start with questions. So I saw some discussion on Discord about homework questions. So let's start with those.
I have a question on 4C. I'm not exactly sure where to start with this one because there's three prepositions that are not quite like a simple A is true or A is not true. I was wondering if it would be possible to, in a direct proof, make an assumption about the conclusion, like, well, if B is true, then I can start working on it.
So you can do that, but everything. So let me pull this up on the screen so we know what we're talking about. So looking at like 4C here, you could suppose B is true, but everything that comes after that is contingent on B's being true. And so there's nothing you can do after that that's going to prove B, because everything you write depends on B. With an indirect proof, if we assume not B and we can prove a contradiction, then we can say therefore B must be true. But there's no way once we suppose B is true that we can prove that B is true. And so this one is definitely trickier. Anybody else have some ideas about this?
Would it be possible to do like disjunctive simplification of A or B? Maybe? Like, if A or B, then A? Or is that not possible?
So there is no disjunctive simplification, but there is a conjunctive simplification. So if you know that P and Q are true, you know that P is true. So that's the simplification sense. There's an addition where we know that P is true, then we know P or Q is true. But disjunctive simplification, we also need to know, P or Q is true and P is false, and therefore we've got Q. But whoever asked the question originally mentioned that we didn't. These were more complex than we sometimes see, and we didn't have just A is true or B is true, right? But we can get to where we have a very simple proposition using this idea of simplification. So we know that if P and Q are true, then we also know that P is true. So since we know that C and D are true, we also know C is true and we also know D is true. So if we know that C is true and we know that D is true, does that help us make some progress?
Well, if C is true, that means the case of the A infers not C, because not C would then be false. And for that statement to be true, that means that A would also have to be false.
Right. So if we can go from, so this is our work area. If we can go from C and D to C, and we know A implies not C, that's enough to tell us that A can't be true. Because if A were true, not C would have to be true. And we know that C is actually true, which means the negation of C is false. So yeah, from here, if we do conjunctive simplification, we can get to C. And if we use that and this together with contrapositive, that'll get us not A. And what can we do with not A?
If not A is true, and that means with, I believe that's the A or B.
Mm-hmm.
Since we know that not A is true, that means that A is false.
Right.
For A or B to be true, B would have to be true then.
Right, exactly. So that's good old disjunctive simplification, right? That says if A or B is true and say A is false, right, or not A is true, then B's got to be true. Or, you know, in sort of common terms, if we know this is true and A is false, well, B's got to be the one that's true. If we know this is true and B is false, then A's got to be the one that's true. So we can put this together with A or B, and that'll get us B. So then it's a matter of you know, writing it out formally and numbering your propositions and writing the justifications for each step and so on. But that's a path to the solution. What about an indirect proof?
We always start off with B naught, yeah?
Mm-hmm. Start off with B naught. And how can we put that with something?
Well, I would then stick that into the A or B, thus concluding that then, okay, so then A must be true.
Yeah, perfect. So another one of these disjunctive simplifications. And then once you've got A, this just kind of screams out, hey, let's go ahead and get the negation of C. And if you know the negation of C is true, that tells you C is false, and that's going to generate a contradiction, because this tells us that C and D are true, so C has to be true. And so a few steps and a bit of fancy wording, and you can get to where you can show not C and C are true, and this is false. And so if we start off with not B, we can eventually prove false is true, and that's a contradiction.
So I have a question kind of relating to this,
Mm-hmm.
another question. It was the one that was talked in the Discord about the, let me find which one. I think it was
Number 2.
Is this the Q and not Q implies P?
Yeah, it was Q and not Q.
Okay, let's see what we got.
When do we say, okay, the state, like the difference between like the statement being true and the value kind of thing? Because the kind of the output of the implying one, the A, therefore, if A then C,
Mm-hmm.
that statement is true when conditions are met. But then the difference between output and then the truth of the statement.
So keep in mind, every one of these is a proposition. It's a declarative statement with a truth value. So is this F, that's a proposition. Right? It's a declarative value with a truth value. It's just that the truth value is always false, no matter what else happens in the universe. But it's still a proposition. I could also, at any point in my proof, write down T, because that's a proposition that is always true, so I could always include that in my proof if I wanted. And A, similarly, right, is sort of like a value instead of, you know, a Boolean expression, but ultimately it's a proposition. This is a proposition. This is a proposition. So maybe think about that in terms of what are these sentences that we write at each line of the proof, and see if you can convince yourself that they're all the same thing. There's not really two types of things we're working with here.
I think it's the fact that, like, oh, we you say that A or B is true, and C and D is true. When you say, oh, this is true versus this is a thing. Because like in the one with Q, not Q, I feel like it's more like saying, oh, there's Q, and there's also not Q, rather than saying, oh, Q is true, and also not Q is true. Which the confusion is when is the difference?
I think it's up to you as the writer of the proof. So let's play with that one a little bit. So Q, not Q, implies P. So certainly we can write down the hypotheses. So we can write down Q, we can write down not Q. So we know that the hypotheses is that both of those are true. Yeah, this one's a little weirder. So, oh, this says prove with truth tables though. But if we think about what this means, yeah, this is kind of different from questions 3 and 4, where you're asked to write proofs of things.
You mentioned in Discord that Q and not Q imply all prepositions.
Yeah.
I think I know what you're getting at, that you know, if a hypothesis in a conditional is false, then what the hypothesis is implying is then the conditional is true, right?
Yes, the conditional is true. Now the conclusion might be true or false, but the conditional itself will be true. So let's put this
It's
down.
real backwards thinking.
Yeah, it is. I'll stick with false and true. Well, go ahead and shoot me an attendance ping right now if we didn't already do that. And as far as I know, my videos will get uploaded right after class. I'm wireless now instead of a hard wire for the time being, but the speed seems to be okay. So like the 224A lecture got uploaded fine. So hopefully lecture recordings for this will go up shortly after 2. But we'll see how it works. All right, so there's the truth table for a conditional, right? And the conditional is always true except in the case where a hypothesis is true, conclusion is false. So so if we made a truth table for this, right, what we would find is that this left-hand side is always false because Q and not Q is always going to be false. And so it doesn't matter what the value of this column is. If this first column, if the hypothesis is false, the conditional is always going to be true. And that's why even though P is not mentioned anywhere else, right, we know that that conditional is going to be true.
So is the reason why we just treat this a little differently is because we're doing a truth table instead of just writing out a form of proof?
Yeah, yeah.
Okay.
But it is weird that Q and not Q implies that I won the lottery, you know. And technically that's a true statement. I got one number out of like 18 numbers, so I guess I did win the lottery. But you know, Q and not Q implies any proposition that you dream up. Q and not Q implies that 1 equals 3. And that almost makes sense because it's, you know, we have this sort of kind of intuitive notion that if something was both true and false, you know, we'd be in Wonderland and maybe 1 + 1 would equal 3 and apples would fall into the sky when they fell off a tree and things like that. And that's kind of the sense in which false implies anything. But it is one of the weirder things of propositional logic. But for the homework question, since you're doing a truth table, right? There's a Q, and then there's Q, not Q, implies P. And if Q is false, Q and not Q is false, and the false implies, doesn't matter if P is true or false, that's going to be true. And if Q is true, then Q and not Q will be false, right? Because they can't both be true. And if Q and not Q is false, it doesn't matter whether P is false or true. The conditional is still going to be true. So there's the truth table. All right, other questions? All right, so let's just dig into more proofs. So we talked about fallacies. We talked about the basic idea of a theorem, right? A statement that can be shown to be true. And we described two main approaches, direct and indirect. Direct, where you start off with the hypotheses and you work logically till you reach the conclusion. Indirect, where you start with the hypotheses, but you also assume the negation of the conclusion and you argue to a contradiction. And then you say, well, something must be wrong. It must be that negation of the conclusion was wrong, so the conclusion must in fact be true. And a lot of times one direction will feel a whole lot more natural than the other. And so let's play around with some numbers. And I want to work with the notion of even and odd numbers. So we're only going to deal with integers for the next however long. And let me give you a definition. So an integer n is even if it can be written as n equals 2 times k, where k is also an integer. In other words, an even number is twice some other whole number. So 10 is even because it's 2 times 5. 6 is even because it's 2 times 3. 0 is even because it's 2 times 0. And negative 100 is even because it's 2 times minus 50. As long as you can write your number as 2 times some integer, that number is even. And then the other possibility is an integer n is odd if it can be written as n equals 2 times some integer plus 1. So one more than a multiple of 2. And you can probably convince yourself every integer is either even or odd, and it can't be both, but it's got to be exactly 1. But these are the formal definitions that we'll use when we do proofs about things being even or odd. And if I wanted to, I could write this, there exists a k in Z such that n equals 2 times k. Or I could say there exists a k in the set of integers such that n equals 2 times k plus 1. So there's a more succinct definition of what it means for n to be even or odd. But just with that definition, we can prove some interesting statements about even and odd numbers. So let's do some theorems. So if n is even, then so is 3 times n. So 6 is even, 3 times 6 is 18, that's also even. 100 is even, 3 times 100 is 300, that's also even. So I mean, it feels like, you know, this is plausible, but we can prove this pretty rigorously. And like a lot of these proofs, it's really just a matter of using the definitions and putting them into, you know, kind of a formal framework. So let's look at an example proof. So proof. Now this is a conditional. If n is even, then 3 times n is even. That would be more formal than saying so is 3 times n. So then 3n is even. So that's the hypothesis, that's the conclusion. When you want to prove an if-then statement, start off with the hypothesis, prove that, you know, if you assume this, you can conclude that. So my first statement is going to be n is even. And my reason, that's the hypothesis. Well, that's kind of it. That's as far as I can go with what I've got written on this page, because I've used everything that I know from the hypothesis. I wrote down n is even, I said that's a hypothesis. Where can I possibly go from here? Really, the only option is use your definitions. Since n is even, there exists some integer k such that n equals 2 times k. That's a proposition. And if n is even, this proposition is true. So I'm going to go ahead and write that down, because I'm allowed to write down anything that's true based on what I've already written. So I'm going to say there exists some integer k in Z such that n equals 2 times k. My justification for that is going to be definition of even. So working with the definition.
So we can use that almost like it's a law of logic.
Mm-hmm.
It's more of a law of math, right?
Yes, exactly.
Okay.
All right, at this point, we need inspiration. So I'm going to mark an area over here. I'm going to say ignore. And I'm going to kind of like think out loud in this section of my paper. And what I want to do is I want to show that 3n is even. That's my goal. If I can somehow get to a point where 3n is equal to, you know, is an even number, I'm done, right? And again, I'm going to go to the definitions. I'm going to say, well, if 3n is an even number, then it must be twice an integer. So all I have to do to be able to show this is show that there exists a k such that 3n equals 2 times k. If I can do that, then I can say, and that's the definition of being even, so that means 3n is even. But I'm going to put a warning here. Which is, in this case, don't reuse k unless you really mean the same k. And I've already decided I'm going to use k in step 2 of my proof here. This is going to be the integer such that n equals 2 times k. And really what I've said here is there needs to be some integer such that 3n is equal to that, but I don't know if this k is going to be the same as that k. So I'm not going to do that. I'm going to say, let's show that there exists a j in z such that 3n equals 2 times j. This is almost, you know, a nitpicky detail, but it trips up so many proofs. So this is saying that, you know, this value of k is the integer such that 2 times that is equal to n. And if I use k somewhere else in this proof, it's got to be that k that when you multiply by 2 gives you n. So right over here, when I'm thinking about what it means for 3n to be even, I'm just going to use a different variable. And say there exists a j such that 3n equals 2j. So if I can show that, I'm basically done. I have to write it up, but I'm basically done. So here's the million-dollar question. Does anybody see some way that I can write 3n as 2 times an integer?
Well, the way I would go about it, since we already have an equality of n and 2k, I would then basically multiply both sides of that by 3. So then we have 3n is equal to 3 times 2 times k. Then I would then rearrange the variables because of, I think it's one of the properties, I think it's association?
Commutativity.
So then, commutative property. So then it's 2 times 3k, set 3k equal to j. And the one thing that stopped me was, how do I go from saying, hey, this is basically the same as the definition in a formal way.
Okay, good, excellent. So just sitting here, how do we write 3n as 2 times an integer? There's really no way to do that. We need something more. But we have exactly one other thing. We have the fact that we've already asserted that we can write n as 2 times some integer. And even if you don't know if this is going to lead you somewhere, give it a shot. Plug in this version of n, 2k, into n right here. And since n equals 2k, 3n is 3 times, you know, instead of n, we write 2k. And stare at it and fiddle with it, and if you rearrange this is 2 times 3k, which is 2 times this thing 3k. And 3 times k, if k is an integer, 3 times k is going to be an integer. And so this little derivation lets us write 3n as 2 times an integer. And then we'll be able to say, okay, since 3n is 2 times an integer, 3n is even. So that's the thinking out loud part, the ignore part. And so now we take that and we try to turn it into a continuation of our formal proof, and we're almost going to work in the opposite direction now. And the reason why you choose to write a step, that's up to you, right? You need to justify why that proposition is true, but you don't need to justify why you decided to write this proposition. And it could come to you in a dream, right? You could find it floating in the bottom of your cup of tea. That's all totally legit, right? As long as you can explain why each proposition is true, it's a valid proof. So for whatever reason, right, over here, we just decided to write down, hey, 3 times n equals 3 times 2k. And that's just, you know, substitution using step 2. Nothing up here says anything about 3n. That's okay. I could write, you know, 1 plus 1 equals 2, and that's totally valid. So 3n equals 3 times 2k. Because n is equal to 2k, I substituted that value of n from step 2. And so I can say 3n equals 6 times k and 3n equals 2 times 3k. And that's, you know, just algebra or arithmetic. Or, you know, you could use commutativity, and 3 times 2 is the same as 2 times 3, but the point is you get it into this form. And now we're going to do something, and this can be a little dangerous. You can abuse this pretty easily, but I'm going to make the observation 3k is an integer. Okay, how do we know 3k is an integer? Because k is an integer, that was asserted up here, and I'm going to say properties of integers. In particular, we're using a property called multiplicative closure. It says if you multiply two integers, you get an integer. Well, 3 is an integer, k is an integer, so their product is an integer. But we're just going to say properties of integers. And as long as you don't misuse this reason, that's fine. Now, if you try to state that, you know, 3n is even because of properties of integers, I'm going to say you skipped some steps. But mostly we'll use to say, you know, if you add two integers or you multiply two integers, you end up with an integer. That's the main property we care about. We could try to prove that, but that's a nightmare. Proving that integers are closed, because you have to get into what it means to be an integer. So we'll take this as a valid proof to show that 3n equals 2 times 3k, and 3k is an integer. And really at this point, we can simply state 3n is even. And the reason is definition of even combined with steps 3 and steps 4. And if you look at step 3, what's it saying? 3n is equal to 2 times 3k, and this is saying 3k is an integer. And the definition of even is that your number can be written as 2 times an integer. And that's what steps 3 and 4 together tell you. 3n is 2 times an integer. That's enough to say 3n is even. You could make it a little more formal. You could set j equal to 3k and state that j is an integer, and then you could state that 3n is equal to 2 times j, and then it would look, you know, almost exactly like the definition of an even number. But this is enough detail for this class. So we've started with n is even, and we proved that 3n is even. What's the last thing we have to put on our proof? We need one more line.
QED.
There we go. Let's write down QED. That says that's the end of the proof, and we've shown what we were asked to show. So at this point, the person reading your proof would go back to the original thing you're trying to prove and say, oh yeah, we're trying to show 3n is even. Hey, how about that? That's what they showed. All right, that's a good proof. So that's an example of a direct proof. In this case, you know, playing around with even and odd numbers. Most of the proofs we do involving evens and odds are going to look very similar to this. Certainly most of the direct proofs. And in particular, there's going to be some point where we need to do something that may not be directly obvious from what we've been given. Here the idea was, okay, so let's substitute n with 2k, and then let's switch these around so that now this is 2 times something else. And there's almost always going to be some kind of step, and really everything before that step is generally going to be kind of, you know, almost something that'll write itself. It's going to be putting down hypotheses or, you know, basic properties of those. And then everything after that step is going to be kind of, coming down the other side of the hill and coasting to the finish line. And it's really this one step in the middle that will take most of the brain power and the trial and error. All right, so let's do another one. So here's a theorem. If n is let's see, if n is odd, then n squared is odd. All right, so help me out here. What's a good first step of this proof, or a possible first step of this proof? Good starting proposition.
Definition of odd.
We could we put a step before that?
I guess it's n is odd.
Yeah, let's start with the hypothesis. And then let's do the definition of odd. So there exists and I don't have to be bound to K, so I don't know, I'll pick a C. There exists a C such that n equals 2 times C plus 1. And that's the definition of odd. And remember, with these existentials, these variables are just placeholders. I could say there exists a heebie-jeebie contained in the integers such that n equals 2 times heebie-jeebie plus 1. And it's exactly the same proposition. So I'm okay just using a C here. All right. What could we try for a third proposition?
Well, I would kind of replace n in the n squared. Or I feel like replace the n in the n squared with the 2c plus 1.
Nice. So I'm going to write n squared equals 2c plus 1 squared. And that's just substitution using our value of n from step 2. All right, well good. Now we've got something more to work with. So let's go ahead and expand this. So this is just algebra. Just in quotation marks. But dust off your algebra neurons, right? And this is FOIL, right? So 2c squared plus 2c plus 2c plus 1. So now we've got n squared is equal to all of this. And maybe at this point I'll do an ignore section. And mostly what I put over here is where am I trying to get to? What am I trying to show? Right? I want to show n squared is odd. And if I go back to the definition, right, show n squared equals 2 times something plus 1, where this something is an integer. This is my ignore section. I can be very informal. I can draw doodles, whatever I want, right? I want to show n squared is 2 times something, that's a whole number, plus 1. So any ideas how we can go from this to 2 times something plus 1?
Well, if we show that the 4c squared is going to be even no matter what c is because it's multiplied by an even number. Basically, we can knock that down to like 2, we call c squared some variable perhaps. Or we put a c squared, so we say 2 times c is therefore even. And likewise, 4 times c is also even. And that leaves us with even plus an even
plus 1 becomes an odd, you could say that r even plus an even is another, you can call it some new integer if you want to call it, x plus 1, or, that's effectively where we're going with that.
So that sounds really good, although let me ask you, how do we know that an even plus an even is even? It is, you're right.
A definition of an even is 2 times an integer is even, right?
If something can be written as 2 times an integer, then that something is even, right? So, yeah, go ahead. So we can write this as 2 times something, and we could write this as 2 times maybe a different something. How can we show that sum is 2 times something? Well, you need to somehow factor out those 2's and combine these somethings. So you need to take this first number and write it as, 2 times k1, and take this number and write it as 2 times k2, and add them, and then factor out the 2, and so on. So you actually have to do some work to show that, but it is doable. That's like a whole separate subproblem in itself. But your goal in doing that is, if I understand you, you're trying to take this and turn it into this form, right? And you're using the fact that these two pieces are even.
Yeah, that's my intent.
Cool. So that feels like a good direction to go in. And we can actually do it a little easier than what maybe you were thinking, which is, we can write 4 as 2 times 2, right? We can do more than just say that this is even. We can actually write this as 2 times 2c squared, and we can write this as 2 times 2c plus 1. So that's just more algebra. And now we can factor out this 2. And that's more algebra, but this is exactly the same expression as that. I've just pulled the 2 out and combined those together.
Well, and we can just say at this point that if c is an integer, that must be an integer on the side. And
Yeah.
therefore, it doesn't matter what integer it is, it has to be an integer because we started with integers, and therefore 2 times an integer is even.
There you go. So 2c squared plus 2c is contained in an integer, and this is where you can say properties of integers. Because it's repeated application of this idea of closure. 2 is an integer, c is an integer, so 2 times c is an integer. C is an integer, 2 is an integer, so 2 times c is an integer, times c again is an integer, and an integer plus an integer is an integer. So it's several steps, but we'll combine those and just say, since c is an integer, this follows from properties of integers, as well as step 2 where we said, sorry, this should have said there exists a c contained in the integers. That's the definition of odd. So this is contained in the integers, and again at that point we can simply observe n squared is odd, and that's the definition of odd, together with the fact that n squared is 2 times this thing plus 1, and this thing is an integer. And so that's a good proof for n squared is odd. And probably before I would do this, I would try it out first, 1 is odd, 1 squared is 1, that's odd. 5 is odd, 5 squared is 25, that's odd. -3 is odd, -3 squared is 9, that's odd. Do a plausibility check, and sometimes in that you'll start to get a feel for how you might prove it. But this is a great proof for n squared is odd. All right, questions about this?
Is this more like some of the rougher proofs we'll do in this course?
Some of the what proofs?
Some of the harder to do proofs.
Yeah. Yeah, in fact, there's some homework questions. We might actually end up doing some of the homework questions here. That's okay. But yeah, this is very similar to questions you'll see on homework and questions you'll see on the exams. There's almost always a few questions about, you know, even and odd numbers and proving things like this. So those were direct proofs, and as I say, they kind of follow a similar structure. There's sort of a preamble, there's a post-mortem, and then there's something in the middle where something really cool happens that connects those two steps. Here it was this substitution of 2c plus 1 for n to let us write this, and then it just kind of like, you know, goes from there. So those are direct proofs. The other thing you'll encounter with these is an indirect proof. And why sometimes we do direct and sometimes we do indirect can be hard to say. But here's an example of a similar sounding question that's going to work really well with an indirect and be really hard to do with a direct. So here's another theorem. So this is an indirect proof example. If n squared is even, then n is even. So let's be clear on what it is we're trying to prove here. If the square of a number is even, we claim the number itself that you squared must also be even. So think of any square. 64, that's a good square. That's an even number. The thing it's the square of must be even too. Well, it's the square of 8. 8 is even. 100 is a useful even to know. A useful square to know. 100 is even, and it's the square of 10, and 10 is even. And all that this is saying is that if n squared is even, n must be even. Now 25 is a square, but it's not even. This proposition says nothing about the nature of n in that case. This proposition only says if the square of n is even, then n is even. Everybody clear on that direction? So if we wanted to prove this, we might do something like this. So we could start off doing what we've done. First, let's state the hypothesis. N squared is even, and that's the hypothesis. And then we could use the definition of even and say there exists a j in the set of integers such that n squared equals 2 times j. That's the definition of even. And now we've written n squared is 2 times j, and we want to make a statement about n. So we could try to take the square root. The square root of this side would give us n, but I don't know what we could say about the square root of 2 times j. Because we don't know anything about the square root of j, and we know the square root of 2 is not even a rational number, as we saw on Wednesday. So that's going to be kind of confusing to try to do anything with. And if you play around with this, it's pretty hard to find a direction to go from step 2 to get to a step 3. So you fiddle around with this and you scratch your head for a while, and maybe you don't find an obvious direction. And so you change gears. And you say, hey, let's try an indirect proof. Alright, so how do we do an indirect? Remember, we negate the conclusion and we try to find a contradiction. So let's do this. Let me state the hypothesis, which is n squared is even. And that's the hypothesis. And now I'm going to negate the conclusion. Right? We know the hypothesis is true. I'm assuming this. I'm assuming n is not even. And if from there I can get to a contradiction, then I know that this proposition 2 must be false. Because if it's true, I get to a contradiction. And proving that this is false is the same as proving that this is true. Right? If this is false, then that's true. And that's what I'm trying to show. I'm trying to show n is even. Well, what can we say about n if we know that it's not true that n is even?
It's odd.
N has got to be odd. Well, we haven't actually proved that, but I did tell you that, you know, every number has to be even or odd, and if you work with the definitions, you could probably show that without too much work, unless you were trying to prove it to someone very picky. But we will take it as given in this course that every integer is either even or odd, and it's exactly one of those. And so here I'm going to say, you know, definition of even and odd. And you don't have to say it must be 1, but I'll just put that there to remind us why I did this, right? Under the definition of even odd, every number is either even or odd. If it's not even, it's got to be odd. All right, unless I say using what we've already proven in class about even and odd numbers, don't make the following leap of faith. But if I say, you know, using what we've already done today, prove this, well, you can come back to this page and you can say, hey, you know what, if n is odd, I can prove n squared is odd. Now this is not something we can just brush under the carpet and say properties of even and odd, right? If I ask you to prove this on a test, right, you got to prove it, right? But let's suppose we've just proven that as the first part of a test problem, right? We've shown that if n is odd, then n squared is odd. Well, what can we write here? What's a good step 4 that we could write?
Would you then write the definition of odd?
Or no.
You could,
Since we already did all that.
but we've already,
did all that work, and we just say, you know, prove n, if n is odd, then n squared is odd.
yeah. I'm just going to go ahead and say n squared is odd. And the reason for this, let me put this in a different color. Either prove this first.
You can just use the proof you already did of the last theorem as your justification. Right?
Yeah. So if you were doing this on a test and I had first said prove this, and then I asked you to prove that, you'd be totally fine. You'd say, you know, see the previous part of this test. But if out of the blue you're asked to prove this, right, don't assume that you can assume if n is odd, then n squared is odd. If you're not sure, ask if it's like on a test.
Could you could you perhaps say theorem if n squared is even, then n is even as a justification, because we know that's true?
We don't know that this is true yet, though. But once we show it, then we could build something from that. Yeah.
Oh, I'm sorry. I meant the other theorem. Oops.
Oh, this one?
Yeah, that one.
Yeah. If you've just proven this, you can use it. Right? And in this case, we just proved this as the prior problem, so we're okay going ahead and using it here. But if you're just working and you're asked to show this, then you need to show that n squared is odd, since n is odd. In other words, once we show something in class once, you don't get to use that on a test and say, well, we already proved this. Right? Which I don't think most of you would do, but occasionally I have a student who tries to do that. So. But in this case, we just showed if n is odd, n squared is odd. Well, step 3 was the proposition n is odd, so I can go ahead and write step 4, n squared is odd. Right? And in this case, we just proved this. So what's our step 5?
Well, if it's odd and even, then we have a contradiction.
There you go. There's our contradiction. And the contradiction is statements 1 and 4. This says n squared is even, this says n squared is odd. Therefore, n is even. So the 3 little dots mean therefore. Therefore, n is even. And then we can say QED, that's what we were trying to show.
That would be the n squared, right?
This?
Yeah.
No, so n squared is even was a hypothesis. So we were already assuming n squared is even. But then in step 2, we assumed that not n is even. And we reached a contradiction, which means that negation was incorrect. And so, in fact, the thing that we negated is true. In other words, n is even is true. And that's the whole secret to the indirect proof, right? We are showing n is even by showing that if n is not even, something ridiculous happens. And so n must be even. Does that make some sense?
Yeah, that makes sense.
So most of these proofs will be either direct or indirect, and this one, like I said, it feels very hard to come up with a direct proof. It just nothing jumps out as like, oh, let's just do this and then we'll be done, right? Whereas an indirect proof of this follows pretty painlessly. And so a lot of proofs will have a preferred direction. Now some cases, like in the homework, right, you're asked to do both direct and indirect proofs, because that's practice.
Why? What does the crosshatch symbol mean again?
That's just a symbol for contradiction.
Okay.
And it means, hey, at this point we have a conflict. If you wanted to write this more formally, we could write n squared is even and not n squared is even. And that would be a statement of propositions 1 and 4. And then we could use one of our page 58, 59 gizmos. And we could say P and not P is equivalent to false. So that's a negation law. And so we could write false. And that's a negation law. And then false is the quintessential contradiction. Right? Remember, every line of your proof is true. It follows from what you've written so far. And once we write false, we've just proven false is true. And that's you know, the most contradictory contradiction that's possible. All right, so that's an indirect proof, and they'll generally flow like that. And sometimes it's challenging. Well, a lot of times it's challenging to sort of know where to put the rigor, the precision in these proofs. So I've tried to be, you know, pretty formal in these examples, and sometimes it's hard to know sort of where to put that formalism. So let me do a different proof, and let's think about this. So let's do theorem. And this is not dealing with integers anymore. So if n equals a times b, where n, a, and b are just real numbers, then a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Now, we haven't done a lot with real numbers, we haven't done a lot with square roots, so we're going to kind of go a little touchy-feely here. But I want to do this for the sake of exploring the mechanics, the machinery of an indirect proof, rather than rigorously proving this in a court of very uptight mathematicians. So if some number n is the product of two numbers a and b, the claim is that a has to be less than or equal to the square root of n, or b has to be less than or equal to. And so think about this. Suppose that n is equal to 100. And we write 100 as a product of two things. This claim is that one of those things must be less than or equal to 10. So, you know, what is 100? Well, it could be, you know, 1 times 100, could be 2 times 50, could be 3 times 33.3, could be 4 times 25, could be 16 times 6.6, could be 25 times 4, or 50 times. There's lots of ways you can write 100. The claim of the theorem is that no matter how you write it, at least one of these numbers is going to be smaller than or equal to the square root of 100, namely 10. And you know, the closest you can get to this is you can write 100 as 10 times 10, and both of these are 10. But if you try to make one of these slightly bigger, the other one's going to go slightly smaller. And that's a hint to how we can actually prove this, right? This idea that if you write n as the square root times the square root, right, and you try to force one of those to be bigger to violate this condition, the other one's going to get smaller, and it's going to satisfy this condition even more strongly. So that suggests maybe doing an indirect proof. So let's try an indirect proof. So statement 1, I'm going to do n equals a times b. That's the hypothesis. Statement 2, I want to negate the conclusion. So I'm going to suppose not a less than or equal to square root n, or b less than or equal to square root n.
Now we can use De Morgan's, right?
Excellent. don't try to do this in your head. We've got a theorem. We've got a buddy named De Morgan, right? Let's use De Morgan's theorem. And I'm going to do this on a piece of scrap paper over here. I mean, I would do this as part of your proof, but I already muddled up my scratch area. But let's do De Morgan's theorem. So De Morgan's theorem says the negation of a disjunction is equal to the conjunction of the two negations. So P is the proposition that A is less than or equal to square root of n. Q is the proposition that B is less than or equal to square root of n. So the negation of these two propositions should be identically the negation of this ANDed with the negation of that. Well, the negation of this is A is bigger than the square root of n. And the negation of this proposition is that B is bigger than the square root of n. So if you're not absolutely sure about that, I would put that somewhere on a sidebar, or maybe, put a line here and put it in here so that I can see it and know how you got to that. But once you've got that, now we can state, A is bigger than the square root of n, and B is bigger than the square root of n. And that's De Morgan's theorem. And at this point, we would need to use a property of real numbers and inequalities and stuff that we learn in other classes. And this is where I'm saying sometimes it's not clear how much to assume, but you can always ask, right? But we know that there's this property of positive real numbers, that if A is bigger than X and B is bigger than Y, then A times B is bigger than X times Y. And this only works if A, B, X, and Y are all positive. If they're negative, funny things happen. But using this property and these two propositions, this proposition and this proposition, I can write the following. A times B is bigger than square root of n times square root of n. And so properties of positive reals along with proposition 3, which shows this and this. And can anybody see a contradiction at this point?
At that point, A times B is not equal to n.
Yeah. So how would we write that? Why is A times B not equal to n?
Well, we can then write A times B is greater than n, and then you just write the sign for contradiction 1 and 5.
Yeah. So we've just shown A times B is bigger than n. That's a contradiction between propositions 1 and 5. Because A times B is equal to n, but it's also bigger than n. Or another way to do that would be substitute n for A times B and make a new proposition which says n is bigger than n. And that's the contradiction that we just saw here. So either way, we've got a problem, right? Therefore, right, so this was negation of conclusion. Same deal. Since this proposition is false, this proposition is true. And so we can write that proposition: A is less than or equal to square root of n, or B is less than or equal to square root of n, and that's what we were trying to show. And so there's your proof. All right. Let me do one more proof. And then Wednesday we will switch gears and talk about some number theory, and we'll come back to proofs part 2 after doing a unit on number theory. But before we leave, let me do something I promised you, which is prove something about the cardinality of the real numbers. And the goal is to prove that there's a fundamentally bigger infinity of reals than there is of integers. So here's the theorem. There is no one-to-one mapping from reals, or let's go from integers to all reals. So to say that two things have the same cardinality means we can make a one-to-one mapping from one set to another. If you have, you know, all the hotel rooms at Hilbert's Hotel and you have all the guests, if you can find a one-to-one mapping from that first set to the second, they have the same cardinality, the same size. Which is why when a new guest shows up, you can move everybody down one room, you still have a one-to-one mapping. And when we said that there were fundamentally more reals than there were integers, what we were saying was that there was no one-to-one mapping. If you start putting real numbered guests into integer numbered rooms, you're not going to be able to account for every guest, right? You'll fill up all the rooms and you'll still have real numbered guests left over. So saying that these don't have the same cardinality is basically saying that there's no one-to-one mapping from the integers to the reals. And we can prove this with a proof by contradiction. So statement 1, suppose, let f of I be a one-to-one mapping from the integers to the reals. So pick an integer, f gives you the thing that it maps to, the real number. And this is our assumption, we're going to argue to a contradiction. And once we reach a contradiction, we'll have to conclude, hey, there is no such function f, which means there's no one-to-one mapping from the integers to the reals, and that'll conclude our proof. All right, got the basics set up? Yeah.
Can't we map all of the integers to reals?
Yes, but you end up with reals left over.
Right, okay.
So that's why I put the all in there.
Got it.
Okay. All right, so how are we going to do this? So I'm going to do a simpler problem. I'm going to go from the set of positive integers to all reals. That's a simpler problem because there's fewer positive integers. And we know the positive integers and the set of all integers have the same cardinality, right? Because you can put the odds, you can put the negatives to odd numbers and the positives to even numbers. So let's just work with positive integers. And let's suppose we have a one-to-one mapping from the set of positive integers to the set of reals. So we're going to make a table. And here's what our table is going to look like. In row 1, we're going to write down the real number corresponding to f of 1. And so this is going to be some number, and let me make it even more simple. Let's just try to map to the interval from 0 to 1. Right? Certainly if we can map to all the real numbers, we can map to the numbers between 0 and 1. So let's keep this simple. Let's just map to integers between 0 and 1, to real numbers between 0 and 1. So every one of these numbers is going to be 0 point followed by something. All right, so you've come to me and you've given me a function f, and you say, hey, this function f will take every integer to a real number between 0 and 1, and every real number gets mapped from somewhere. So I don't know, maybe 1 maps to, you know, pi divided by 10. And maybe the real number 2 maps to, you know, 0.5. And maybe the real number 3 maps to, you know, 0.66666, and so on. And maybe the real number 4 maps to, you know, 0.1, and so on. Whatever they map to, the claim is that this function, you know, maps all these positive integers, each of them to a real number, and that eventually any real number that you think of between 0 and 1 appears somewhere in this table. All right, that's what this hypothesis claims. And we can get a contradiction out of this really easily. So what we do is we construct a new real number between 0 and 1. And we construct this number as follows. We start with a 0 point. And the first digit of this new number is the first digit of this first number plus 1. So since this is a 3, we're going to write down a 4. The second digit of this number we're constructing is the second digit of the number in the second row. This is a 0, we're going to add 1, this is going to be a 1. The third digit of the number we're constructing will be the third digit of the number in the third row. This is a 6, so we're going to write down a 7. The fourth digit will be the fourth digit of the number in the fourth row plus 1. So 1, 2, 3, 4, that's a 0. So we'll write down a 1. And if we have a 9, we'll add 1, we'll write down a 0. So we keep doing this and we construct this number, which I'm going to call B for bad. And guess what? This number that I've just synthesized cannot appear anywhere in this table. It deliberately cannot appear in this table because of the way I made it. Suppose you claim that, you know, this is actually the number in row 25. So you claim this is 0.4171, blah, 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 blah. I can say, no, that's not right. You know why it's not right? Because the 25th digit of this and the 25th digit of that are not the same. In fact, the 25th digit of B is 1 more than the 25th digit of the number in this row. So B can't be f of 25. Well, maybe it's f of, you know, 1007. Nope, if you look at f of 1007, its 1007th digit is different from the 1007th digit of B. And any number that you think of, any I that you claim f of I is equal to this, you can prove that that's not possible. Because this will differ from f of I in the ith digit. And the only conclusion you can end up with is that this real number B does not appear anywhere in this table. In other words, there's no integer I where f of I is equal to this. And since this is a number between 0 and 1, our hypothesis was that, you know, there is some integer that maps to that. Well, we've just proven there is no such integer. And so the conclusion is that this hypothesis must be, this assumption must be wrong. And the conclusion is there is no function f that maps from the integers to that interval of real numbers. And that's how you prove there's no one-to-one mapping. And that's why the integers have smaller cardinality than the reals. And this is called a diagonalization argument. And it's diagonalization because we're kind of doing something by going down the diagonal of this table, and we're very deliberately kind of, you know, putting a little twist in to the generation of this number specifically to cause this contradiction. And this was controversial. This was why Cantor was bad-mouthed and denied jobs and things like that, because it's so deliberately trying to mess things up that some people felt like, well, this doesn't prove anything because you tried to make nonsense, But it is a valid proof, right? This is why Copernicus actually didn't get in trouble for claiming that the Earth revolved around the sun, because his proof was rejected, because he devised an experiment that would prove his result, and people said, well, you can't do that. You started off by trying to prove this, and you came up with an experiment to do that. It wasn't considered a valid method of experimental discovery. But this is, considered a valid logical proof. So yeah, so there's more reals than integers. So there you go. I wasn't just making it up.
So I have a question for you. I've seen this proof before, kind of.
Mm-hmm.
But the person who is explaining it mentioned that if you tried to do this with integers or fractions or other stuff like that, you'd wind up proving that the cardinality of those kinds of numbers are all the same.
Mm-hmm.
Versus with the real numbers, what we just proved here is you can basically make a diagonal that's different from every single number.
Right. Right. And well, it's hard to formulate a proof like this for integers, for like a mapping from one set of integers to another set of integers, because an integer, I think it's partially because an integer has a finite set of digits, and we're really, really depending on the fact that there's an infinite set of digits to a real number. So that we can say, whatever number you claim I is, whether it's 10, gazillion, in the 10 gazillionth place we'll find an error. And I think if you try to do this with integers, the fact that you might not have a 10 gazillionth place in that integer breaks that down. But it's an interesting question to understand why you can't do this with integers. But that doesn't prove that they have the same cardinality. To prove that, you need to come up with a one-to-one mapping, and for the set of all integers and the set of even integers, that mapping was easy. Just take your integer, multiply by 2. And now you've got a one-to-one mapping. Every integer goes to an even, every even comes from an integer. For rationals, we never did this, but we got a couple of minutes left. For rationals, you can do the following. So cardinality of rationals. Make yourself a table. Let's do P and Q, and we'll do 1, 2, 3, 4, 5, 6. And keep going. And let's write down at each of these spots the fraction P over Q. So this will be 1 over 1, 1 half, 1 third, 1 fourth, 1 sixth. And you get the idea. And there's some repeats in here, but if we can map this set one-to-one with the integers, then we know we can map the rationals one-to-one. Because we're mapping even more things, right? We're mapping 4 over 4 and 3 over 3 and 2 over 2, when in fact those are the same number. And to find a one-to-one mapping between this set and the set of integers, all we have to do is start off here and follow a pattern. Let's come down, and then let's go up and go across and come down and go down and go up the diagonal and come across and come down, and so on. And the integer mapping will be This is the integer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on. And you can make the two claims without too much controversy. One, every integer corresponds to a rational. In particular, if I start here and I follow this path and I go out n steps, the number I end up at, that's what I'm going to map n to. And since every rational will sit on this table somewhere, right? Every rational is a p over q fraction, so if I go down p and across q, that rational will be somewhere here, and eventually this curve that I'm drawing will cut through there, and when it does, however many steps I took, that's the integer I'll map to it. And that's a well-defined one-to-one mapping between integers and this superset of the rationals. And so that shows that the cardinality of the rationals can be no bigger than the integers. It could be smaller, but since every integer is a rational, it's got to be bigger than or equal to, and so it's actually the same. And this is where sometimes the cardinality of the integers, we talk about that as being a countable set. And a set that's countable is a set that has the same cardinality as the integers because you can count them. Right? Counting is a good way to find a one-to-one map between integers and elements of a set. If you can say this is the first, the second, the third, and the fourth, right? That's a one-to-one mapping. And that's really what's happening here is we're coming up with a way to apply an ordering to these things. So that's another unfinished business from set theory that we've just finished. All right, so those are just freebies for fun. My office hours tomorrow morning are late. They're 8:50 to 9:50. They're noted on the schedule. So I won't be there at 8:30, but I'll be there at 8:50, I hope. Keep working on the homework, and Wednesday we will start looking into some number theory, and we'll leave propositional logic for a week or so, and then we'll come back to it and get into some really beefy stuff. All right, cool. Have a good one. I will see you next time.